Hello everyone, welcome to Computer Science 226, lecture number 18. Today we'll be talking about the trees. That is a very important fundamental concept in computer science. I highly recommend learning that as good as you can, because it will repeat in all other classes, in the majority of the classes. It will definitely come up with the interview. It's one of the most basic and most important, most fundamental data structures in computer science. Okay, so let's do it. Okay, trees. Before we get into that, so I want to quickly talk about something which we didn't cover last time, about maps. Okay, so here we have singleton map. Hold on, yeah, okay. So singleton map. What is a singleton map? Yeah, so singleton list, singleton map, and in general, singleton is basically it's a data structure which contains only one item. Okay, so for example, singleton list, that is a constructor. That method creates an immutable list containing only one item. So whenever you see something which is called singleton, that means that's a data structure which contains only one item. For example, if it is a singleton map, that means it is a map with only one item. If it is a singleton list, if it is a singleton set, right? So it's the same thing, like list or set with only one item. One item and one item only. That's called singleton. Okay, so what do we have here? Singleton object set, right? So that returns an immutable set containing specified object. So basically it creates a map, it creates a set, okay, which is being returned with only one object, the one which you pass in the constructor. Same thing is singleton list, right? It returns the list. Singleton map, right? So you pass in key and value, and then it returns the map. And then, yeah. So there are also in the collections class, there are also three constants: empty set, empty list, empty map, right? So they spelled exactly that way. And can you guess what they do? They create empty set. So it is a set with nothing in it. So it's very important to understand that empty set is not like it's nothing, not like it's a set which doesn't exist. No, it is a set which contains nothing in it. So imagine if you have an array with the size of 0. The array still exists, there is just nothing in it. Okay, so fundamentally, it's something which you're probably unlikely to use near time in the future, I guess, in your career, but sometimes it can be very helpful. Anyway, yes, so it's possible for a set, for a list, for a map to be empty, to have nothing in it, or to have only one element. Okay, so if there is only one element, it's called singleton something. Okay, yeah, so empty set, empty list, and empty map. These collections are immutable. What does immutable mean? Immutable means that once it is created, it cannot be changed. So for example, if strings in Java are immutable, what does that mean? That means you create in a string, you assign something, for example, like hello world, right? And then you cannot change a letter or a character in that string. If you want to modify the string, you have to create a completely new string, copy the content, and modify that content while you're copying. Okay, so once you create a string, assign some value to it, that string is not mutable, it's not modifiable, it's impossible to modify that. Okay, so the class also provides singleton object, singleton list object, singleton map. Okay, create an immutable map containing only one single entry. Okay, I hope that makes sense. What else? Collections. The collections class also provides 6 static methods for returning read-only views for collections: unmodifiable collection, unmodifiable list, unmodifiable map, unmodifiable set. Okay, so all of them can also be created as unmodifiable. Again, so modify means to change, unmodifiable means something which is not changeable. This type of view is like a reference to the actual collection, but you cannot modify the collection through a read-only view. Okay, you cannot modify the collection through a read-only view. So read-only, it's also actually a term in computer science that means you can, read-only means you can only read, but you cannot change, you cannot write to that, you cannot delete it. Read-only. Attempting to modify a collection through a read-only view will cause unsupported operation exception. Okay, so if you create an unmodifiable collection using the collection, okay, it will return you an unmodifiable collection and if you try to change something in it, you will get an exception, unsupported operation exception. Hope it makes sense. Anyway, tree. So what is a tree? Tree is a fundamental, it's a very it's a fundamental, very important data structure, which usually looks like something like this. So you have a node, you have something which is at the very top, and that's called the root, okay? And it's connected to the elements below. In this case, we have 2 elements below for each one of them, okay? In this case, we have also like at most 2 elements below, right? So it can be numbers, it can be letters, it can be digits, it can be, I don't know, students, professors, it can be like any other object, just whatever you can think of, right? But it's important that elements in the tree have to be of the same data type. For example, tree of strings, tree of integers, tree of doubles, tree of letters, tree of some like a rectangle, like tree of some kind of shapes, a tree of I don't know, triangles, something like that. Okay, so again, it is a data structure, so which means that it is a way to store and keep data structure, okay, tree. So why is it called a tree? Is because basically, like, if you take a look at this and then if you kind of like flip it upside down, right, then in this case it will kind of remind you of a tree. So this will be root, right, which will be at the very bottom of the tree, and then this will be kind of like branches. Okay, so let me maybe show you in Paint. So Paint online. Let me show you. Okay. So it's possible to have a tree like this with 3, where each node would have, let's say, 3 children, right? And then we'll have connections, so like this. Okay. Yeah, so this guy would also have 3 connections, like 3 children, but none of them are valid. Okay, so it's possible that, yeah, so this node is connected to this 3. This node is connected to also 3 nodes, but they are null, so they don't exist. So they're connected to nothing. Okay, that's possible. And also, this guy is also connected to 3 other nodes. So that's valid as well. Yeah, the most important thing is this. It's impossible to have a connection like that. Okay, so that's not allowed. And it's impossible to have like double connection like this, right? So tree is kind of like a graph. Later we'll be talking about the graphs, what they mean in computer science as well, okay? But that's a simplified version of a graph, tree, okay? So most importantly, it's a hierarchical data structure which goes kind of from up, okay, that way. Yeah. It's also allowed to have maybe like any number of children as well. So you can have like 4, you can have 6 in one tree. That's very unpopular though. So for example, you can also say that, hey, like I want this guy to have like 4 children. Okay. And technically that would be allowed. Okay. And I want, for example, this guy to have no children at all. Technically that would still be allowed. Okay, that's what you have to know so far. That'll be enough. Okay, so that is a tree. Tree would be a data structure with the root value and subtrees. Okay, so subtrees of children with a parent node represented as a set of linked nodes. Okay, so basically this node is linked to this one is linked to this one, and that one. This node is also linked to this one and that one. Okay, so yeah, think about a stack. Okay, so if that's the top of the stack, and then you may not only go down to one node, but you can actually kind of go down left, go down right, and then do the same thing there. Okay, but what's important though is that you, at any moment of time, right, if you would like to access some node in the tree, some element in the tree, you would have to start you always have to start from the root. Okay. You always start from the root. You always start over here. It's very important. You always start over here. Okay, so you cannot immediately access this node. You have to start over here, then go down. Okay, so then go down to the middle, and then go down to the right. That's the way you can access this guy. But we'll talk about it later a little bit. Anyway, so a very, very popular particular case of a tree is called a binary tree. A binary tree is a hierarchical data structure where every node is either empty or consists of an element called a root, okay, and two distinct binary trees called left subtree and right subtree, either both of which may be empty. Okay, so binary tree is something similar to that with one restriction. You're only allowed to have at most 2 children. You're allowed to have no children, that's fine. That's fine, but no more than 2. Okay, so that's the root. On the very top we have a root. Here we have one node. Okay, so we have this guy is called the root. Now, if that is a root, everything on the left, that is called a subtree. That's called the left subtree, and the right child and its children, all of its children and the children of the children, that's called the right subtree. So the binary tree is a data structure which contains a root with 2 subtrees. Left subtree, okay, so this whole thing is a tree. This is a left subtree of the root, and that's the right subtree of the root. So those are good technical terms. Children, okay, so the elements which are linked to the node and located at the bottom, those are called children. So children, left subtree, right subtree, tree, those are all technical terms which you need to know. So I'm not making them up. They are that's what they're called in the literature. Those are technical terms. Okay, so that's called the binary tree. Basically a tree where every node is allowed to have at most 2 children. It's possible to have 1 children, for example, left children, like this. Okay, it's possible to have 2 children, but you're not allowed to have 3 children ever. So this would not be allowed, because that would create 3 children for this guy. That's not allowed ever. So that would not be a binary tree. Okay, now we'll be talking about, okay, cool. So some terms. Okay, so we have 2 distinct binary trees called left subtree and right subtree, either or both of which may be empty. It's possible to have a tree of 1 node. Okay, in this case this guy is a root. Okay, and if it has 2 subtrees left and right, both of which are null, so they do not exist. Well, they exist, but they're connected to null, or you can say they don't exist. That's also fine. But anyway, so there is only 1 node. There is only 1 element in that tree. That's called the root. Okay, so only root. Technically, sometimes it's also, depending on the context, it's also possible to have a binary tree with no nodes. So completely empty binary tree. So basically, I don't know, like imagine you have so that's your that's your binary tree, and you would have a root, but that root just doesn't exist. Okay, so it's empty. So like empty binary tree would be a tree where there is not even a root. So the root which should be there, it doesn't even exist. That would be an empty binary tree. Okay, so left subtree, right subtree. Now let's talk about some definitions. The length. So what is the length? The length of a path is the number of edges in the path. Okay, so first off, let's talk about the path. What is a path? So let's say we have a bit deeper binary tree. Okay, and now the sequence of edges connected to each other is called a path. So for example, I want to have a path between this node and this node. Okay, so that will be the sequence of edges. That's the first edge, that's the second edge. Basically the sequence of jumps which you need to take between the root or between some node and some other node. Okay, so that will be a path. What I just did in red, that will be a path between the root and the path between, so a path between the root and this node. Okay, that's called a path. Now, what is the length of the path? The length of the path would be the number of edges in the path. Okay, I hope that's clear. The depth. So the depth of a node is the length of the path from the root to the node. Okay, so in this case, what is the length of this path? 1, 2, 3, 4. How many edges do we have? 1, 2, 3, 4. How many connections? 4 connections. So there are four edges. The depth would be 4. Okay. The set of all nodes at a given depth is sometimes called a level of a tree. Okay. So if like I take this, so this, okay, that is a set of nodes which have the same depth. Okay, so the depth would be, so the depth would be the length of the path from the root to a current node. Okay, so for example, depth of a tree, depth of a node. Okay, so for example, what is the depth of this node? The depth of this node would be 2, 1, 2. Why? Because there are 2 edges between that node and the root, 1, 2. Okay, so the set, a collections of all the nodes which have the same depth is called a level. So these guys basically, like, I mean, if you draw a horizontal line, there will be a level. These guys, they all have the depth of 2, right? So the distance between each one of them and the root of the tree is 2. Okay, so 1, 2, 1, 2. 1, 2, and also 1, 2. So this guy is already on a different level because it takes 1, 2, 3 jumps to make it to this node from the root. Hope it makes sense. Okay, so siblings are the nodes that share the same parent. Okay, so siblings are like brothers. So this guy is a parent, it has 2 children. So this guy and this guy are siblings. Okay, the root of the left is called the left child. Okay. The root of the left subtree is called the left child, the root of the right subtree is called the right child. Okay, so basically, think about this. We have a tree, that's the root, and that is so-called subtree, kind of a tree which is located in the tree. Okay, and what is the root of this subtree? Is this guy, and this guy is the right child of this guy. Okay, and now without the children is called the leaf. Okay, so think about the tree. A tree has leaves, right? So that's basically the ending points. I would say maybe like this guy would be a leaf, this guy would be a leaf, this guy would be a leaf, right? So they're located at the very bottom. They do not have any children. The height of a non-empty tree is the height of the path from the root to the furthest leaf. Okay, so let's say I have this I have this tree. What is the height of this tree? Right, so imagine you're looking at the tree, right? So tree. So imagine I'm looking at this tree, right? So how to calculate the height of this tree? I'll probably go from the very bottom, from the ground. I'll measure the distance between here and between the highest point in the tree, right? And I would just like take a ruler, huge ruler, I don't know. I would just like calculate how many feet it takes to go from here to over here. So similarly, in the binary tree, the height would be the distance between the root, okay, and the furthest leaf. Okay, so over here we have the distance between here and the furthest leaf. So that's probably the furthest leaf of the tree. Okay, unless I don't know, this guy. Well, unlikely. Well, technically, again, usually the furthest leaf would be the very top, right? So that would be the height of the tree. So in binary trees, in trees in general, in computer science, the height would be the distance between here and the furthest leaf. So this guy is not the furthest, this guy is, right? Why? Because its depth is the biggest. It takes like 4 jumps to get here. Okay. The height of a tree that contains a single node, right? So the height of the tree which contains only the root is 0. So imagine you have like this, only one node in the tree, it doesn't have any children. So what's the height? What's the distance between the root and the root, right? So what's the difference between root and itself? Okay, so it's 0. There are no edges in between. That's why the height of this tree is 0. Okay, moving on. Now, Yeah, binary tree. Okay, so the question is, okay, we know what this data structure is like. Now, the question comes in, how can we create it in Java? In Java, there are separate classes which you can use to create a tree. However, it's very, very useful to do something which we did to linked lists and double linked lists in the queues to create it from scratch. For example, in this case, here's how we can do that. We can create nodes, okay, very similar to the way we did it like last time with linked lists, okay, and we can make that node connected to two other nodes. So remember when we're talking about the queue and the linked list, right? So we had a node, it had one connection to the node which was next, okay, and that was called .next, right? Now when talking about the tree, we have a node and it needs to have two connections, to the right child and to the left child. Okay, that's basically kind of the difference. So it still has the element, it still has the value, for example, let's say 60, and it has two connections, two links to two children. Okay, if that link, if that subtree doesn't exist, if it's empty, right, then we need to connect it to null. Remember when we're talking about the linked list, right? So we had a node connected to some other node, and then if that node was the tail, if that was the finish line, that was the end, it still needs to have a link, right? But the word link was pointing to null. Null means that that's it, like there is no like way of going further. That's it, that doesn't exist. Hope it makes sense. Okay. Yeah, so each node contains a value and two links named left and right that reference the left and right child respectively. How do you search? Yeah, so the question is, for example, oh yeah, so that's binary tree, and then we come to binary search tree. Okay, binary search tree. So, okay, so we have something which is called a tree, which is a data structure where you have the root and some combination, some number of children. Okay, that's called a tree. We also know what a binary tree is. That's basically when you have a node and which can have at most have two children. Okay, now there is other like kind of more specific case of a binary tree, which is called a binary search tree. And it like this in short, it's called BST, binary search tree. Okay, how's that different from binary tree? So that's a binary tree, and a binary search tree is exactly the same thing, okay, which would have one value per node, okay. Now the only difference is this. For example, okay, so imagine, yeah, so it's going to have numbers. Okay, so it's going to have numbers. Let's say 50. No, 50. Okay, so the root will be 50, and then all the elements on the left should be less than the root. Okay, and all the elements on the right should be greater than the root. Okay, so in this case 50 has 25 and 70. Okay, then 25, the left child of 25 needs to be less than 25, so let's say 10. The right child from 25 needs to be greater than 25 but less than 50, right? So for example 35. 70, okay, the right child from 70 should be greater than 70. Okay, so it's, let's say, I don't know, 100. The left child from 70, let's draw the links first. Okay, now the left child from 70 needs to be less than 70 but greater than 50, so let's say 60. Okay, so that's called a binary search tree. It's still a binary tree, right? Each node can contain at most two children, but with that exception, if you go to the left, then all the nodes you have in that tree are less than the value of the root. If you go to the right, all the nodes are greater. Okay, so basically, if you draw a vertical line, let's say I'll draw a vertical line. Okay, if I draw a vertical line through 50, that means all the nodes, all the elements on the left side from that vertical line are less than 50. All of them. That's the rule. It should never, 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 never be not true. Okay, so it's 25, 35, 25, 35, 10. Okay, if I draw a line through 70, same thing. All the nodes on the left from 70, all of them should be less than 70, and all the nodes on the right should be 100. Okay, so just don't be kind of. It's very easy to make a mistake, thinking like, for example, okay, I want to create a node on the left from 100. I'll make it, let's say, I don't know, 60, right? 60. So unfortunately, that would be incorrect. Why? Because yes, 60 is less than 100, however, 70 is less than 60, right? And on the right from 70, we're only allowed to have elements greater than 70, and 60 is not greater than 70. So 60 should be somehow on the left from 70. So that's not allowed. That's the wrong position. That's not a binary search tree. That violates the most important rule of a binary search tree. That's a mistake. You should never do that. Okay, hope it makes sense. Yeah, so here I have the picture, I have the code for the tree node. So for the class called node, okay, we're using generics. For the homework, we'll be creating the node of integers, okay. Protected E element, so the value of the element, right, left and right, and the constructor, okay. Now the question is, so why are we talking about that? Like, why is that useful? So that data structure, binary search tree, is extremely useful in computer science. So here's one of the reasons, the biggest reason, probably the biggest reason why. Okay, so let's say I have this binary search tree, and I want to, well, I need to deal with the 760. So let's substitute that with something more meaningful. Let's make it 80. Okay, so 80 is allowed. 80 is less than 100 and greater than 70. Okay, so let's say I want to search for, I want to see, okay, so for example, is, I don't know, 60, does 60 exist in this binary search tree? Okay, so how do I search for an element in the binary search tree? That's very easy to do, and it's a lot quicker than in the array. So here's how I do it. Okay, so the only element I have access to is 50. That's the element on the root. That's the element on top. Okay, so 50 is the first element. I compare my element which I'm looking for, which is, let's say, 60, to 50. Okay, if 50 is less than 60, that means if 60 exists in this binary search tree, then it gotta be on the right from 50. Okay, that's why I go to the right. Then I compare my element 60 to 70. If 70 exists in this binary search tree, that gotta be on the left from 70. Then I go to 60, then I compare 60 to 60, I see a match, I return it. I return true, I found it. Okay, now let's say I'm searching for 90, which doesn't exist. Okay, so let's say, is 90 there? I'm comparing 90 to 50. Okay, and 90 is greater than 50, that's why I have to go to the right. Then I'm comparing 90 to 70, 90 is greater, I have to go to the right. I'm comparing 90 to 100, 90 is less, I have to go to the left. Then I'm comparing 80 to 90, 90 is greater, I go to the right. So I go, so I go somewhere here, okay? And then what do I see? I see that that node doesn't exist. That means that 90 is not in the tree. It just doesn't exist there. So that's why, yeah, so like it's very, very easy way to search in a tree. Okay, so that's the code for it. Yeah, so yeah, what I would like you guys to do for the homework, I would like to read the book, like to read about the binary search trees. Okay, I want to do I want you to do like more of that. And then for the homework, we'll basically be creating a binary search tree class of, let's say, integers or doubles or some other data type. Yeah, so we'll be creating the binary search tree in Java. Okay, we will not be using the class which is provided by the Java developers. We'll create our own binary search tree. Okay, then next lecture I'll be talking a bit more about binary search trees. Okay, I'll give you a little bit more of detail how it works, like advantages and disadvantages. Yeah. Okay, cool. Hope you guys enjoyed that. Until next time. Bye.